Welcome to this explainer. I'm the lead developer of the Sexos microkernel, and today we are talking about a pretty wild scenario. Imagine Tux, our favorite chaotic, interrupt-driven, state-mutating Linux penguin, crashing our hyper-strict, lock-free, deterministic, multi-server microkernel sex party. It is literally the ultimate architectural clash. You see, Sexos is a pure mathematical reducer. We expect perfect causal ordering. But Tux just wants to run wild and break things.
But here's the thing, we don't kick him out. We actually need him. Specifically, we desperately need his massive library of hardware drivers. So instead of bouncing him at the door, we've designed this incredibly intricate, airtight containment strategy. We drop him into a containment cage we call Tuxedo. Inside Tuxedo, he totally thinks he's having a wild time running free in a monolithic kernel. But in reality, we are strictly orchestrating his every single move without him ever realizing he's completely trapped.
So how do we pull this off? Let's get into part 1, the domestication strategy.
Now, when we talk about domestication, I know exactly what all the hardcore OS developers tuning in are screaming at their screens right now. You're wondering, why not just rewrite all those legacy Linux drivers from scratch in pure, mathematically safe Rust? It's a totally fair question. Honestly, for a long time, that was basically the holy grail of microkernel design.
But we realized pretty quickly that rewriting all those drivers in Rust, it's a complete Sisyphean trap. Chasing the massive, ever-changing Linux driver tree is a total fool's errand. You're literally never going to catch up to the hardware vendors. So that means our only viable path to hardware dominance is wrapping the existing C code, strictly constraining it, and translating its outputs into our own model. We don't replace Linux drivers, we domesticate them.
And to pull that off, we built our containment cage, Tuxedo. Now let me be super clear. Tuxedo is not a POSIX layer, and it's definitely not a Ring 3 kernel. What it is a deterministic device driver environment translation broker. You can think of it as a deterministic driver VM equipped with privileged escape calls. Essentially, it acts as an emulator of chaos layered over a substrate of order. It feeds the legacy C code exactly what it expects to see, while we enforce absolute mathematical precision underneath the hood.
Okay, moving right along to part 2, the Tuxedo containment cage.
Think about the massive contrast between illusion and reality here. What Tux actually thinks is happening is that he's running totally free inside a monolithic C kernel, grabbing memory whenever he wants and firing off wild IRQs. But the reality? He's actually running as an entirely untrusted guest program locked inside a strict deterministic VM. He's heavily walled off within physical Intel MPK or PKE protected domains. So every single memory access is actually happening inside a heavily gated segment of our single address space OS.
The real magic happens through a very precise 5-step pipeline. First, we start with the unmodified, untrusted C code of the legacy Linux driver. Then, that flows safely down into the Tuxedo ABI shim, which completely fakes out the kernel headers. From there, it passes into the Tuxedo runtime core, which is our actual truth layer, before being semantically compiled by the SexDrive event model. Finally, it hits our bare metal Sexos capability kernel. It is a completely airtight filtration system.
To make sure this actually works, we have to enforce some absolute non-negotiable invariants. First, the drivers are strictly treated as untrusted guests, completely walled off by those Intel MPK domains I mentioned. And this is crucial. There is no asynchronous control flow allowed whatsoever. None. On top of that, any direct memory access, or DMA, is mapped directly to capability objects. This guarantees that chaotic C pointer pollution can never, ever leak into our core OS state graph.
Let's dive deeper in part 3, stripping away the chaos.
Using our ABI mapping model, we are able to surgically intercept all that legacy chaos. For example, when the C code calls camlock, Tuxedo just smiles, fakes it, and allocates memory from a local Ring 3 bump slab instead. When the driver calls request_IRQ, we trap it and seamlessly route that interrupt straight over to an IPC queue. And what happens when it tries to grab a spin_lock? We fake that entirely too. We literally compile it down to a NOP, just absolute nothingness. Because inside our cage, preemption just doesn't exist.
That perfectly leads us to the very core of our domestication strategy, the total eradication of fake immediacy. You know, in normal Linux, hardware interrupts can just violently rip control away from the CPU at any given microsecond. Not in Sexos. Here, hardware interrupts are simply not allowed to interrupt anything. Instead, they are captured as raw data events, dropped into an inbox, and they are only ever executed when Tuxedo's strictly serialized deterministic tick comes around to consume them.
But of course, legacy drivers inherently expect interrupts, right? If we just turn them off completely, the driver's going to crash. So we have to play a little psychological trick on the C code. We call it the reentrancy illusion. We carefully, deliberately lie to the Linux driver. We simulate reentrancies to make it believe it was preempted and then resumed. This perfectly preserves its internal locking assumptions, and we pull the whole thing off while never actually yielding the CPU core. We are completely in control of time.
Let's jump over to part 4, zero-copy capability substrate.
Now, you might be wondering, how do we extract ultra-high-performance memory operations without having to copy data all over our single address space? Because let's face it, if we have to copy data out of the cage, we instantly lose the performance war. Well, the answer is 0. That is exactly how many times we copy data. We achieve true zero copy in this architecture by mapping DMA allocations directly to Sexos capability memory objects. The hardware literally pushes data right into a buffer that the rest of the OS can instantly read without ever breaching that strict isolation boundary. It's a massive shift from the legacy Linux way. Traditionally, physical memory addresses are just indiscriminately leaked directly to the driver. But with our zero-trust Sexos DMA model, the driver only ever gets an opaque, cryptographic DMA token and a highly restricted IOVA handle. Our kernel entirely hides the actual physical memory from the driver.
Let's quickly walk through this DMA capability bootstrap sequence because it's pretty slick. First, the Rust layer requests I/O. Then, the kernel allocates the physical memory. Crucially, the Intel VTD IMMU maps that physical region directly to the device. Next, we create a capability object, and finally, we pass that opaque token over to the Virtio engine. The hardware is physically caged in. It absolutely cannot bypass the IMMU.
And honestly, this brings us to our absolute greatest victory so far, the fully proven extraction of the Linux Virtio block driver. We successfully stripped away 1,200 lines of messy kernel state and boiled it down to just 6 pure math functions. We literally physically severed the C code from the machine. It can't cause page faults anymore. It's completely decoupled from OS state. All it does now is take a device frame and mathematically output a result. It's beautiful.
So, where do we go from here? Let's wrap up with part 5. Taming bigger beasts next. Getting storage working was really just the beginning. Now we're escalating from simple storage straight up to complete userland domestication. Enter Snowseed. Snowseed extends Tuxedo's DDE translation broker. If Tuxedo cages the kernel drivers, Snowseed is what cages the userland. It acts as our POSIX compatibility shim, essentially an algebraic reducer. It intercepts all those chaotic legacy Linux system calls and cleanly bundles them up into perfectly deterministic IPC send events that our pure capability kernel can easily digest.
Here is how our roadmap is shaping up, separating what we've already proven from our next major targets. We've totally nailed Phase 1 with the Virtio Black extraction proof of concept. Next up, in a matter of months, we'll evolve into full Linux NVMe driver containment. After that, we build out Snowseed to catch the full scope of Steam Proton game syscalls. And finally, Phase 4, the ultimate boss fight, wrapping those massive closed-source NVIDIA and AMD GPU drivers right inside the Tuxedo boundary.
Which naturally leads us to the ultimate gaming translation question. I know every systems engineer looking at our microkernel is wondering right now, can we actually run heavy, stateful, wildly chaotic Steam Proton games deterministically inside a hyper-strict, lock-free architecture?
The answer is an absolute yes, and we do it by treating legacy C code not as some active participant in the OS, but merely as a dumb, wire format serialization library wrapped tightly in our strict FFI. Because Snowseed bundles those messy POSIX syscalls into completely deterministic IPC send events, our Sexos algebraic reducer can digest and run those Steam games with pure, mathematical, reproducible precision. Those chaotic games literally just become pure data.
We successfully tamed the chaotic Linux penguin by dropping him into a party governed by absolute strict capability invariance, and we did it without him ever even realizing he was constrained. It completely proves that legacy C domestication and strict Rust containment can live in perfect, beautiful symbiosis. So I'll leave you with this thought. Now that you know exactly how we've mathematically caged this chaos, what chaotic legacy code are you going to domesticate next in your own rigid systems? Thanks so much for joining me on this explainer.